Thanks so much for the opportunity to talk to you about securing data with obfuscation. First, a little bit about who I am, besides being apparently extraordinarily unlucky at webinars. My name's Tim Gorman. I work in technical services at Delphix. Delphix provides products for data virtualization and data masking. Been there for 3 years. Prior to that, I was Oracle DBA for about 20 years. And then prior to that, a C developer on VMS and Unix for about 14 years. So overall, pretty good career. I've got a couple books published, 2 on Oracle data warehousing, 3 on database administration with Oracle, and then 1 on Oracle SQL. I've been an ACE director for about 5 years. I belong to the Oak Table Network, and I'm proud to have been a board member of my local Rocky Mountain Oracle user group now for 22 some odd years, currently treasurer. I've also been involved with the ODTUG, Oracle Developer Tools user group, on their board. I live in Colorado in the US, married to Kellen Potvon Gorman, better known as DBA Kevlar, and between us we've got like 5 kids, quite the mixture. So at any rate, enough about that. Mainly I want to talk about how data security is going to become a far bigger task in our world, coming very soon. It always has been a big enough task, but for the most part, it's been a problem mainly for the infrastructure teams, providing firewalls to protect our internal systems against the outside world, making sure to use the right utilities to transfer data back and forth between systems. Mostly it's been, again, the role of the infrastructure team, but there are developments that are happening in the world today that are going to make it part of the average database administrator or even application development and testing teams. So it's an extraordinarily large problem, and it's going to become something huge. Around the turn of the century, the last century, we had another big revolution, if you will, in data security. In the U.S., it was called Sarbanes-Oxley, and there were similar laws around the world. But basically, it had to do with separation of duties to make sure that one person couldn't do bad things, quote unquote, within the systems that support a business. And those laws were a little bit arcane, and they took years and years to finally develop, but they finally come to fruition. And for most large companies, separation of duties and siloing and preventing employees from being able to do things, or a wide range of things, I should say, only things within their specific silo or job description, is pretty widespread right now. But now we've got even more changes coming along. And I want to talk about the problem and what a full solution looks like. So you've seen stories about data breaches, going on for years and years and years. This just shows a quick timeline of some of the major data breaches that we've seen over the past 10 years or so. And they seem to be accelerating, and it's true. Data breaches are caused by, usually caused by unauthorized people gaining access to systems. But we saw something just a few years ago that really emphasized the fact that sometimes the problems can come from within. And I'm referring to Edward Snowden. That episode about 4 years ago was a situation where, for better or for worse, whatever you say about his motivations, Mr. Snowden took his position of trust as a systems administrator and distributed data, caused a data breach, of a significant size. At that point, the realization became, and it came out in the open, that, quite frankly, there's a significant amount of liability even from people working internally at an organization, either participating in or even causing a breach. It's not just external forces necessarily, it could also be internal. So, my feelings about the whole thing, again, if you even set aside the moralistic motivations that Mr. Snowden may have had or felt he had, the fact is that the code of honor by which I know I'd played with for my entire career, and everyone I know has played by throughout their entire career, was all of a sudden rendered basically irrelevant. So it's a wake-up call. 2016 was a watershed year for IT in many ways, because at that point, the realization of all the threats and the frequency of data breaches began to reach critical mass. And, as you can, I won't read the slide to you, but basically, we're seeing massive spending ramping up on data security by organizations. In addition, it's not just a matter of corporate policy, but soon it's to become law. And this is going to put some real teeth into the issue of data security and make it a problem that we all have to address. The European Union is out front on this. Starting in 1996, they started a privacy working party, the Article 29 Working Party in 96. And the basic idea behind the Working Party was to provide expert advice regarding data protection. Well, the Working Party eventually published a white paper in 2014, and without losing much time, the European Union devised the General Data Protection Regulations, GDPR. Look at that. My acronym is incorrect, and I'm going to correct it right here, live. Anyway, the GDPR was adopted in 2016. And basically, GDPR becomes law in less than 12 months. Law, so that if a data breach occurs in any company headquartered within the European Union or doing business within the European Union, is now subject to penalties based on a percentage of revenue. That's big stuff, and that's real teeth. So data protection has always been, but is now a very, very public problem, and something that everybody in IT has to deal with. So from May 2018, next year, again, roughly 10 months from now, monetary penalties will exist. All the previous data breaches that you've seen, you can kind of consider them to be child's play, because all they created was bad publicity, which is bad enough. But now we have actual cash that will be levied as a penalty going forward as a result of GDPR. And how long is it before this European Union regulation is propagated around the world to different countries? After all, it's only common sense. Data privacy is important. So there's a lot of different ways to protect data. When everyone talks about data protection, the first thing that pops to their mind is the physical security around the data center. How do you build a data center for security? How do you prevent people from carting viruses and such in? How do you prevent them from, more importantly, carting confidential data outwards? So it's basically a ring structure: physical security around data centers, network security within and without the data center, but more importantly, at the very source of record for this data, that is the systems, the databases, there has to be data security as well. And accepted by most organizations, encryption of data at rest and data at flight appears to be the weapon of choice against the problems of data security. But the question has become, is that enough? Now, as with any form of warfare, data security involves some of the concepts of divide and conquer. And along those lines, consider the systems that we have within our organizations. Production systems are literally the tip of the iceberg, a small percentage of the total number of systems that we run, because even greater than the production systems are the non-production systems in terms of volume, in terms of exposure as well. So consider that to be the body of the iceberg. Non-production is, even though it's not considered as important to an organization because it's not running the business of the organization, non-production is out there, and it's a larger problem. Many of the recent data breaches that have occurred where data has been leaked is a result of penetration of less protected non-production systems, one way or the other. They have the confidential data from production because most people perform software development lifecycle, SDLC, by cloning from production to non-production. And when we do that, when we clone from production to non-production, we usually clone several times over. That's the reason that non-production is so much bigger. We have a single production system for each application, but behind that production system and supporting it, we've got dev and test and training and UAT and SIT and all, who knows, all kinds of other additional systems. We've got copies of the systems for different projects, for the different sprints within the different projects. Agile programming methods have made this replication of full environments even more of a crisis. So non-production has grown even bigger. But the fact is that many organizations have an estate of data systems that is bigger than they can handle. So divide and conquer. Divide and conquer. The things that we really have to protect is production. We have to protect the systems that are running our business. Non-production, we might be able to split off and handle a different way. Encryption is the way to handle data security in production. The idea that data at rest or data in flight can be, encrypted and made meaningless to outside users is an important concept. And then for those users that are authenticated and authorized, only they're able to decrypt. But for the rest of the systems, the non-production systems, there's no reason at all why there should be any confidential data outside of production. No reason at all, no reason whatsoever. Okay, I'll say, having said that in so absolute terms, there are a few reasons why there might be confidential data outside, but very rare exceptions. So how do we handle that data problem, that data security problem? And the fact is that we need to use the technology of obfuscation or masking to render the data that's outside of production irrelevant by changing the data in such a way that it looks realistic, but in fact it's completely meaningless from the standpoint of identifying or identifying individuals or identifying confidential information. So again, the question comes back, doesn't encryption protect data? Absolutely it does, but you've got the problem of authorization. Okay? If you have a regular production application user, certainly they should be authorized and be able to authenticate, to be able to decrypt data so that they can do their jobs. But now stop and think about non-production uses of data, development, testing, training. Should someone, for instance, be able to conduct training classes using confidential information, allowing people who may not actually become authorized production users to view that data? The answer, of course, is no. Same thing is true if you are outsourcing the development tasks or even the testing of your systems to people outside your organization. Should they be able to view confidential data? And the answer is no. So encryption, even though a greater population is able to authenticate, is authorized to authenticate, they really shouldn't be from a business and liability standpoint. So here's the pop quiz. What happens when a production system is cloned to non-production? And the fact is that what is happening there is that confidential data is being presented to unauthorized users, plain and simple. And they shouldn't see this data, okay? But they have to do their jobs. We can't lock them out from the data. We can't come up with a different way of populating non-production systems for development and testing with data other than cloning from production. I mean, it's been tried to generate artificial data, but the fact is that while applications can be developed with artificially generated data, it can't be tested with artificially generated data. At least it can't be tested realistically. So there really is no other there is no other method of enabling software development without cloning from production. So it looks like I repeated the slide, so I'm just going to keep going. So then how does masking protect our data. Masking is basically irreversible modification of specific pieces of data. Encryption, if you think about it, is reversible with the proper key, when you're authorized and authenticated. But no matter how you're authorized or authenticated, masked data is irreversible. And when it's done well, masked data is difficult to differentiate from unmasked data. In other words, it looks real. It's not enough to simply mask data by scrambling data. Too many things break when that happens. Here's a very simple example. Let's say that you are a documentation expert and you are attempting to write documentation for a new application. Now, part of documentation is taking screenshots. If you can take screenshots of masked data and have it look good in your documentation so it doesn't look like garbage, that's well-masked data. That's a really good little litmus test right there. But the fact is that by using masking on non-production data, we can render all that data completely useless from the standpoint of criminality or any other nefarious uses that people may have. So understand the requirement. With production, we have to be able to reverse the obfuscation on demand. But with non-production, there's no reason to reverse the obfuscation. Okay? So overall, these are the requirements for protecting the vast majority of our data. We've got many of the problems with production data solved with encryption. For masking, it can't be reversible. That's the first thing. The basic idea is once data is masked for non-production, we should be able to just leave it out in public so that anybody can read it if we so desire and not cause any loss of confidentiality. The results must be a representative of the data source. It has to look real and it has to feel real. A real definitive reason for this has to do with something as arcane as the Oracle Optimizer. The Oracle Optimizer will behave differently if the masking of data changes the distribution of data, changes any of the characteristics of data. Also, unfettered randomization of data might also destroy referential integrity, because if we change a column on a row that's being used as a foreign key, if we change that column in the parent table and don't change it the same way in a child table, then we've basically destroyed the functionality of our applications. So the results have to be representative and referential integrity must be maintained. Non-sensitive data doesn't really, or non-confidential data, doesn't necessarily have to be touched, but it might need to be considered if it can be used to recreate sensitive data. Think about this. What if we didn't alter certain aspects of personal data, and then we all of a sudden ended up with a situation where a person is easily identifiable because of some of their secondary characteristics, like their age. 99-year-old person. There are very few of those in the world, and so they're easily identifiable. A person of any physical characteristics that are extraordinary, extremely tall, extremely short, extremely heavy, extremely slender, anything like that might allow towards the identification of people. But most importantly, masking must be repeatable, not just within a single system or application, but across systems and applications. We have to be able to, that's part of the referential integrity problem, but we have to be able to repeat the process over and over again. We just have to be able to. So, looking at the evolution of most masking solutions, most people start off with homegrown scripts or something built into their application that does an attempt at masking or obfuscating data. The most common would be something like a national ID, such as in the US, a social security number, or the Australian national ID, or anything like that, where the most significant digits are masked or redacted with an X, and only a few digits are left unmasked for identification. The problem with that is that some applications or some confidential data might be encoded. It could be that if you stop and think about credit card numbers, for instance, the average 16-digit credit card number has 15 digits that are checksummed to add up to the 16th digit in checksum format. So just simply scrambling data is going to break applications that are performing that check. The other thing about credit card data is that, say, the first digit represents what bank or what credit system the credit card belongs to. I know for a fact that credit card numbers belonging with a 3 belong to American Express, that belong with a 4 belong to Visa, 5 MasterCard, and so on. So all of that secret encoding, has to be preserved. So homegrown scripts are a quick entry level, but the fact is that you're taking on the problem of building something that you can potentially buy that someone else has developed. And the trade-off in investing 1 or 2 person years into a body of work that requires person decades or person centuries of work is a difficult trade-off. So test quality is generally low on homegrown scripts. A person is generally not a subject matter expert who's been asked to do homegrown masking. And again, build versus buy, you're not leveraging with one person doing some simple solutions. You're not leveraging the efforts of dozens or hundreds of people. Okay, so homegrown scripts are the way things start, but usually they graduate to perhaps a more mature solution, perhaps the use of stored procedures that can be that are more like developed software packages. Now, when a organization moves away from simple scripted solutions to more advanced stored procedure or stored solutions, now we're talking about a company that's taking on the responsibility of this kind of functionality for themselves. And really, they might be missing an awful lot. It's the other thing, too, is that it may not necessarily be a portable solution. Someone may develop stored procedures for SQL Server, but they don't port to Oracle. That's a large level of effort as well. So we move on to the next. Now, ETL tools, most organizations have tools like Informatica or Ab Initio or any of the similar types tools, and those are built for data movement, and they can be repurposed rather easily to obfuscate data, either on the fly as they're moving data from one system to the other, or they can be repurposed to do it in place. But the thing is that the simple act of obfuscating data, as you'll find out, is only part of a comprehensive solution. Part of the problem, too, is being able to identify data that is confidential that we're not aware of. And that doesn't necessarily come from such a point solution that's just focused on manipulating data. So an enterprise data masking solution is built to handle all the phases of the project. First, profiling data within our applications to find confidential data, sometimes in places where we don't expect it. Systems generally grow at a fairly rapid pace as people customize. And we might find that data gets squirreled away, confidential data gets squirreled away in places we just simply don't expect. We could end up, encapsulating the data in a large object in a document or a XML file, and it came from another table entirely, and here it is now being propagated into another form of data that's not so easy to parse. We need to be able to find it no matter where it hides. A lot of people do know where their confidential data is, but sometimes they don't realize that it's been pushed to different areas around the system as new applications or new customizations have been built. So we've got different data domains that require different algorithms to obfuscate correctly. Again, simple randomization just doesn't work. We want something that can help us find the obfuscated data, secure it, and then afterwards detect whether or not newly added data has not yet been masked or obfuscated. We have to audit also. We have to prove that we've masked our data. So we have to have a way of doing that as well. So comprehensive solutions are more than just the simple act of manipulating data. So again, profiling first. We have to have a way to scan both the data dictionary of a database as well as scanning actual data within fields, either in a sampled form or in a full scanning form. We have to be able to find confidential data where it resides. We have to be able to identify it, either using keywords or looking for data in specific formats, or even looking for specific data values. We have to have a tool that's able to do that. We then need to produce something like an inventory. At the very least, it would be a spreadsheet that would indicate, depending on different domains of data, such as phone numbers, that's one domain, addresses, that's another domain, email addresses, that's another domain of data. For each types of these domains of data, how are we going to obfuscate them in a sensible way? So we have to come up with that. And then once we've identified all these domains and the algorithms used to obfuscate them or mask them, then we have to find all the occurrences of these domains throughout our applications. And we have to be able to report on that. For securing the data, there are different ways, but for the most part, we make use of SQL and make use of the SQL language in order to obfuscate this. And this comes with its own risks that I'll mention towards the end of the session. Now, even, or I should say more non-intuitively, once we've masked the data, is our job over? And the answer is no. We have to review the data periodically and see if somehow or another the application is inserting new data into the system that is somehow not yet masked or obfuscated. So we have to be able to run an audit against our set of data and make sure that the job's worked, that the data that was modified has remained modified. That's not easy to do. And we also have to be able to, of course, retain a record of when specific items of data were changed, so that if necessary, if a breach does occur, we have to be able to track back how it did occur. Okay. So profiling, again, is all about identifying data. Again, first of all, at the most simplest level, by looking through the data dictionary of the database and looking for columns that are named certain ways that, just at the very basic level, columns that are named certain ways, but also expanding to the point of taking samples of data and looking for patterns or specific values within them that indicate that there might be confidential data. Okay, we have to be able to report on that. This profiling operation, has to be as fast as possible and be able to provide results so that a designer or an architect can review it and again, take action to determine if this is a false positive or whether this really is a new instance of confidential data squirreled away somewhere. So considerations for some of the common data domains that you'll find: credit cards, ID numbers, they usually have embedded logic. Again, as I mentioned earlier, with credit cards, the type of card is usually the first digit. Then the issuing institution is the next 5 digits in some cases. The individual account is a 9-digit number. And then we've got a checksum digit at the very end. We can't, we have to be careful about how we modify this, because certain applications are decoding these credit card numbers and using them. Geographic data is usually encapsulated in multiple fields. It's very common to have a street address, a city, a state or province, a postal code, country, 5 or 6 different columns or fields that might add up to a single lat long, in geographic terms. We have to mask those as a set. Other demographic data might provide what is known as identity leakage. Think about this. If you mask geographic data and it points at a different location, and now in that different location, you now have unmasked data about age, gender, or ethnicity, height, weight, their occupation, anything like that, you suddenly can have some fairly unique individuals showing up in some pretty small populations that makes them stand out. That's identity leakage. We can identify that these people, are who they are just based on some of their secondary demographic characteristics. So we have to be able to prevent that as well. So obfuscation is a science, and it's a big science. And we need to be able to make use of all the sophisticated techniques to prevent people from reassembling identity from secondary information, as well as blocking them from primary identity information. And it's not just identity. I have a customer that, interestingly enough, is a privately held company, and they produce food products. And it just so happens that this private company is so profitable that one of the domains of data they want to obfuscate, that they want to mask, are the quantities and prices of their sales, because they don't even want their own employees to know how much money the company is making. Think about that. Confidential data means more than just industry accepted norms, especially in privately held companies. There are situations there where the private owners, their idea of confidentiality is different, and that's real. So, just talking about one masking product in particular, the one from Delphix, there are 8 built-in, pre-built algorithms for masking. And I just wanted to talk about some of them, just to give you an idea of what's available. The first, and I'll talk about some of these in more detail, but the first one is called secure lookup. It's the most popular technique, and it produces non-unique masked values. So it's got, it's suitable for some domains, not for others. And there's another variant of the secure lookup algorithm called secure shuffle, and that is kind of a customized form of the secure lookup algorithm, but all it's doing is using existing regular data values. So really what we're doing is we're shuffling what's actually there in production. We're just shuffling data values around in a secure fashion. And I'll describe more about what I mean by secure. Binary lookup is another variation for large objects such as images, because the way that we do secure lookup with text can't necessarily be propagated to large objects, again, such as documents or images. Static mapping is another algorithm. Segmented mapping is also extremely popular. And that's an idea, that's something that we've alluded to already, where we take a field and we break it up into segments and mask each segment differently. Or not. We can also hold some values as they are originally and not mask them at all. So segmented mapping is another algorithm. Min-max, ensuring that all values stay within a specified range to prevent unique values from identifying someone. That's that secondary characteristic thing that I mentioned, such as age. If a 99 or 105-year-old person shows up somewhere where they really don't exist, it makes them a little bit easier to identify just because there's so few people at that age. That's an extreme example, but there are similar examples, and especially when you're combining multiple demographic fields together, you can actually pinpoint people. Data cleansing is not really an obfuscation or masking technique, but basically the idea is to put data into a standard format and then apply a masking technique over the top of it. So in other words, regularizing place names, such as St. Louis is a good one, or St. Petersburg, instead of spelling Saint ST or STE or SAINT. You want to regularize it as a certain way. Free text redaction is the idea that we have perhaps documents or large text columns full of data, and confidential data is sprinkled throughout. How do we detect and how do we fix that problem of people's names or identifying information being inside documents? That's what free text redaction is about. And then last and not least is tokenization. And I've just spent some time saying very forcefully that masking is all about irreversible obfuscation. Well, tokenization is about the idea that about generating a token that can actually be reversed, because there are times when you want to present somebody with masked data and they can analyze it, and if they find anything such as if they perform fraud analysis on a set of data, if they find any anomalies, they can pass it back to you, pass the tokens back to you, and now you can decrypt those tokens, so to speak, to find what the real production data values are that they found issue with. So that probably requires a little more explanation than I probably have time for, but the idea is that there is some reversal. And how that's implemented, I can give a little bit more insight into by describing the popular secure lookup algorithm. Okay, so this is one of the 8 algorithms that are pre-built into Delphic's masking, and it's a patented process, proprietary. But let's take an example as way by illustration. So let's say we have a company name, okay, and we don't want that to be in our non-production data. So ANZ Holdings is the name that we want to obfuscate or mask. And let's say that after masking, it comes out as Standard Oil. So here's the process by which it comes out. ANZ Holdings gets translated to Standard Oil. So a lookup table first is predefined. It can either be predefined, it can be predefined from anywhere, but for the most part, the person doing the masking is going to create this list. And let's say they have 500 different distinct company name values. Okay? So the first thing is that we predefine this lookup table and we hold it. Next, we encrypt the phrase ANZ Holdings using, let's say, AES 256-bit algorithm. And it comes out as a certain string that you see here on the screen. Okay? So now that string can now be hashed using an algorithm such as MD5 to come up with a numeric value, such as this number here. Okay? So we've encrypted it, we've hashed it, and then we modulus by the length of the lookup table, which is 500. And it just so happens that this value, modulus by the size of the lookup table, comes up with this value, 117. So the lookup table entry at 117 just happens to be Standard Oil. So think about that, all the different things. A lot of people, production data is stopping at encryption. This is the value that would be seen if somebody didn't have the encryption key. We not only take that, but we then hash it according to another algorithm, could be MD5, and we get another purely unique value, just unique, in other words, to our internal masking process. Well, let's put it this way. I'm not going to say that nobody can crack AES 256, but it would take quite a bit of work for them to crack that encryption algorithm. But then to crack MD5 of the encrypted value to get this hash value, and then to know how big the lookup table is and find the modulus for it to get this index number, and then without having the lookup table to be able to find this reference to it, pretty darn difficult. We're talking about encryption on top of hashing, on top of modulusing, on top of a list that nobody else has. That's pretty difficult. Okay, so that's secure lookup. It converts this value into this value. Now here's the other beauty of secure lookup. How many distinct data values do you think are in our overall domain? Let's just say, for the sake of argument, that in the table that we're masking, the number of different company names is, say, 811. but our lookup table only has 500. So what that means is that several of the 811 distinct data values are going to hash to the very same value in the lookup table. So now a person who is trying to crack this secure lookup algorithm is now also dealing with duplicate results. It's not just ANZ holdings that might mask to become Standard Oil. It could be another data value altogether that masks to Standard Oil. So now think about the difficulties of trying to reverse engineer that. It not only, it's not a one for one when it's unmasked, it's one to many when it's unmasked. Going in one direction, it's always definitive. ANZ Holdings and let's say Cisco Systems, they both mask to Standard Oil. But going back the other way, they could unmask to either ANZ Holdings or Cisco Systems. A really important property to secure lookup. So secure lookup could be used just about anywhere, except if we're trying to mask a unique key, right? Because of this indeterminateness, we might end up with multiple duplicate data values. So we can't use it for values that are supposed to be unique. Segmented mapping. Looking at national IDs, an example being perhaps the U.S. Social Security number, a 9-digit number broken up into a group of 3, a group of 2, a group of 4. Okay, so we could use pre-built, and we have pre-built algorithms for different nationalities and different national IDs. We can make sure to preserve the hyphens, make them irrelevant. We can preserve and not mask the last 4 digits so that people can verify their SOC if they know it, but they can't decrypt the first 5 digits. So we could set it up so that we either map the first and second segments, the 3 digits and 2 digits, to either map to the letter X or to map to new values. So the resulting value could be something like XXX6789 or something completely different. Okay. Account numbers are another method. These would be customized. We don't have anything pre-built necessarily for that, but the whole idea is that your application may have different account numbers, and we can break that up into different segments and preserve some values and use different algorithms to mask others. We could leave some values. We could do some of them with secure lookup, do others with just pure straight mapping. The opportunities abound. Okay. Min-max, again, trying to keep outlier values that can aid in identification, keep them to a mid-range using min-max. Addresses, think about this. You've got an address, you need to obfuscate it. Country, you generally leave that unmasked. But the postal code comes next. You go after the postal code, and maybe you want to stay within a radius, a certain geographic radius, by only masking the least significant 3 or 4 places in the postal code. And you can mask those, using a segmented algorithm, you can mask those with secure lookup. And that means that at least certainly for the US zip code, the last 3 digits only relate to, a metro area. So we can now shuffle people around the same metro area, but just not too far away from where they actually reside, so that the other demographic data doesn't look too crazy. But we can keep them within that radius, and just as an example. And once we've masked the postal code to a relevant value, or at least a realistic value, then we can populate city, state, province, or street address using actual data from postal authorities, by referencing the postal code into that. So we're able to do quite a bit here. A comprehensive solution would also have to be able to add new and customized algorithms defined as maplets. So make sure that your application has that as well. So in the end, you're going to end up with a masking inventory. You're going to have different columns and fields, names, salutations, and you're going to assign different algorithms to mask each one of them, and you're going to be consistent across all applications and systems. So here's the thing. I think you understand now that masking is not something you can just, go out and write a quick randomization algorithm for. It's laborious to develop, and it requires careful discovery, careful design, and then it requires lots of development and testing, even with a comprehensive package. So that kind of careful development and testing requires an ability to rewind destructive testing and to repeat test scenarios over and over again. And it also requires testing against large and realistic sets of actual data. In other words, say production systems. And for that, data virtualization is a perfect solution. Being able to quickly clone off systems, which is the purpose of data virtualization, integrates perfectly with data masking, because data masking is a process that is in need of being able to create copies and rewind and manipulate copies quickly. And also because the comprehensive masking solution has to operate on any data platform, a data virtualization solution itself has to be a solution for multiple platforms, such as Oracle, MS SQL, DB2, Sybase, HANA, and then just flat files and directories, documents, things like that. So the Delphix virtualization solution, which also resides with the masking solution, starts off with a process against Oracle that reads change data. It keeps copies of data changes on an appliance in your data center. And we use the RMAN utility for that to capture changes. Instead of thinking of RMAN as a backup utility, think of it as a change data capture utility. We take a full copy of a source database in the very beginning, and then afterwards incrementally capture changes, again using RMAN. And we store those in the virtualization engine in a very compact form. Then we're able to quickly thin provision copies of that and present it to target servers over NFS. So we're not actually moving a 10 terabyte database off of the virtualization engine to a target system. We're just projecting an image of 10 terabytes. It's still a read-write database as far as Oracle is concerned. And we can do that very quickly to a lot of different systems. So in the footprint, let's say we have a 10 terabyte source database with 10 terabytes of storage on a virtualization engine. We can easily produce within that original 10 terabyte footprint 20 or 30 copies very quickly and easily. Okay, so the overall virtualization solution has two closed loops. We've got one side of the virtualization solution on the source side, capturing changes constantly. The other closed loop is supporting all these targets as read-write independent environments. And these two closed loops don't meet. They don't interfere with one another. Okay. The masking solution is a variation on it. It's another virtual engine that contains all the masking algorithms and logic, and we use it to mask a virtual database. And that virtual database itself is able to be managed very, very easily. We're able to refresh it on demand in a matter of minutes. We can also rewind it or move the database time to at any point in time we designate with bookmarking. So the masking engine, for instance, if we want to test a new masking algorithm or changes, we can bookmark a database to a point in time at the beginning of our test, run our test with the masking engine, and then when that's finished, we can rewind the database back to the bookmark and do the masking test again with any changes that are necessary over and over and over again very quickly. Because masking can take a long time, I sometimes refer to the first virtual database as a gold copy, because we don't necessarily, earlier I mentioned we can quickly and easily make 20 or 30 copies of a database. We don't want to have to do a multi-hour masking process against all those copies. So what I recommend is creating a masked copy called a gold copy, and then producing copies of that as working copies for developers and testers to use. So mask once, and then from that masked image, provision many times. So this masked gold copy is a technique that can certainly be used without data virtualization. But let's look at the timeline here. Let's just assume that cloning a 10 terabyte database takes at least 18 hours using, say, RMAN duplicate target database. So our timeline from the beginning of, create for me a masked copy starts with cloning. It takes 18 hours. And then I have to do the masking on that cloned gold copy. Let's say the masking job to mask all the confidential data within the database, let's say that's 6 hours of processing. So now we're up to 24 hours. And now, because we want to keep the gold copy pristine to copy it again, we have to create our first working copy using RMAN duplicate target database. And again, that takes about 18 hours. And in the second copy, another 18, because it takes a long time. Third copy, 18 hours. Overall, we're talking about, to make 4 working copies of masked data, we're talking about a total timeline of about 96 hours, start to finish. That's without, that's masking and using the gold copy mechanism to create 4 copies without data virtualization. Now with data virtualization, because we're able to create thin copies very quickly in a matter of 15 minutes or less, creating the gold copy takes 15 minutes. The masking still takes 6 hours. There's nothing that data virtualization does to speed that up. So that's still a 6-hour job. But now once we've masked the gold copy, and now we can create 4 extra copies, they each take 15 minutes. That's 1 more hour, for a total elapsed time of 7 hours, 15 minutes. So down from 96 hours to less than 8 hours. And it can get a little bit better than that, because the work performed, or the resources required to create each one of these 4 working copies is so minimal that we can do them in parallel, something you can't do with a massive duplicate target database operation. So if we do that, we've actually reduced the elapsed time by a little bit, down to 6 hours, 30 minutes. So without virtualization, we're talking about creating 4 large size 10 terabyte masked copies, taking 96 hours end to end. But with data virtualization, it takes less than 7 hours. So here's a big gotcha about any data masking package you look at. Whether it's Oracle's data masking, which uses PL/SQL, it creates custom PL/SQL packages with the specified algorithm for all the different data domains. That's using, that's the Oracle package that's used with Enterprise Manager. Informatica, the repurposed ETL tool, extracts data just like an ETL tool. It processes everything in memory, and then it saves the data persistently, again, using SQL. Similar to IBM's 2 packages for data masking. The newer one is called Optim. The older one is called Data Stage. They're both quite popular packages. Again, they use SQL. They extract the data in bulk. They process it in their own application server, and then they push it back using either push it back in place, either using row IDs or inserting it in bulk using bulk operations. And then Delphix has its DM suite. Same thing. We extract the data in bulk, we process it in our own application server, and then we push it back either one of 2 ways. We call it in place or on the fly. In place is basically updates using row ID. So we extracted the data in the beginning with row ID, we masked it, and then we just update with row ID. That's in place masking. There's also on the fly masking, where we essentially rebuild the table. So we select all the data in the table up into our app server, truncate the table, and then reinsert the data back. A couple different ways to do it. But one thing you should note is that all these methods, all these vendors, when they mask, They use SQL. Of course they do. These are relational databases. That's how they manipulate data, using SQL. But what can SQL-based databases do? The fact is that all these packages, Oracle or SQL Server or, Sybase, they all have data recovery mechanisms. They all have the ability to recover transactions that have already been committed, recover the prior data values. That's not a weakness of the masking package, but it's a reality of the databases that we're working on. So Oracle in particular has the ability, even on a masked database, a determined DBA or sysadmin can still retrieve the before masking data values if you're not careful. They can use flashback query or flashback database features to pull before masking data values out of the undo. They can use log miner if they have access to redo logs, and what DBA or sysadmin wouldn't. So, and I'm not saying that we're talking about an Edward Snowden situation here, but let's say we're shipping a copy of our masked databases off to another organization for outsourcing. Those people can possibly recover pre-masking transaction data from undo or redo, or even mechanisms like an audit trail or AWR and ASH. And if you're shipping a backup, I think you all know the internals of how Oracle does an update. Oracle doesn't replace updated columns inside database blocks. They append updated columns inside database blocks, and they mark the old rows within the block as unused. And at delayed block cleanout time, everything is reorganized at that point and consolidated. But just by scanning data files, you can see pre-changed data inside data blocks. So a sysadmin can a clever sysadmin can use block dump utilities to see pre-masking data. So the key is here, no matter which masking, comprehensive or otherwise, whichever masking tool you use, for Oracle, be sure the first thing you do is set your database into no archive log mode before masking. Okay. Another thing, disable any flashback features. Okay. Eliminate or disable auditing and clear out the existing audit trail. That's before you start a masking job. Then you're running your masking job. Again, maybe it takes 6 hours, who knows? It's all dependent. But after you're finished running a masking job, because it's an Oracle database, make sure that you clear out the online redo log files on the database by either doing an open reset logs or an explicit alter database command to clear and reset log files. Make sure to truncate any audit trail or AWR tables, even if you disable them ahead of time. Make sure you truncate them afterwards. Make sure to drop and recreate your undo and temp table spaces because they can contain pre-transaction data. Once you've done all those things, you can be pretty sure that you have covered most of the ways that anybody, even very clever sysadmins and DBAs, can retrieve pre-masking transaction information. There's still some ways. There's no way that we can necessarily clear out blocks, but someone would have to be extremely determined to be able to grab Oracle data straight out of operating, using a file dump utility. So that's where encryption, transparent data encryption, may come in handy. So overall, just to summarize, if you're relying on encryption at rest or in flight as your solution for data security, you haven't thought it all the way through. That's just adequate for production, but really not for non-production. And if you're not yet masking confidential data, you will be soon, because it is already a business liability to not do that. And soon it may become a crime. Also, if you're scripting or writing your own data obfuscation, then you're probably not, all due respect, but you're probably not doing a great job of it, because unless you're a subject matter expert in the area, you're not really considering all the different possibilities. Consider buying buying a comprehensive product. And if you're not using data virtualization in addition to data masking, then you're wasting both time and storage. And really, both time and storage are of the essence these days. So overall, that's what I had to present.
Okay, now